In the previous fragment, we introduced the ring of polynomials. Now let me address some terminology in this connection. And terminology and notations. So for a polynomial f, which is a naught plus a1x plus many more plus a n x to the n, we will call a naught the very first coefficient constant term. So a polynomial is an element of our ring of polynomials. We call a naught constant term. That is maybe just any element of the ring R. Maybe 0, maybe not. Any element is allowed to be a constant term. The last coefficient, an, is called leading coefficient, provided it is not 0. It is also, of course, an element of our ring R. So leading coefficient is the last non-zero coefficient. Among coefficients, there may be zeros, non-zeros, they are all merely elements of R. The last non-zero coefficient is called leading coefficient. If this is 0, so the leading coefficient is somewhere here, the last non-zero coefficient. About notation, let me stress that the textbook uses the textbook writes f of x as an element of R of x. I will consistently use then simply f to be an element of R of x. I will skip always, or almost always, this x in parentheses. One reason to do that is to emphasize a polynomial is not a function. So that is that f is not a function. It is only an element of the ring R of x, which we just constructed. It is a collection of coefficients, collection of elements of R, which we write as coefficients of x. So it is this notation which the book uses is very similar to a notation for a function, especially with the letter f, which the book prefers for an arbitrary polynomial. So let me always write it this way. F is an element of R of x. It is an element of ring, this ring, not a function at all. So now for a polynomial, we define its degree. Degree of a polynomial f is the index of its leading coefficient. Meaning f is a naught plus whatever plus a n x to the n, and a n is not a 0. 0 is 0 in R. Then we say that degree f, that is a notation for degree of polynomial. Sometimes I write f polynomial in parentheses, sometimes not, is n. So this is a polynomial of degree n, provided a sub n is not 0 in the ring R. In this way, the degree is defined for every polynomial except 0. The degree is defined and this is always a negative or non-negative integer. Every polynomial with one exception, 0 polynomial. This is the 0 in R, and this is the same thing as 0 in polynomial ring. This polynomial 0 does not have a degree. For every other polynomial, the degree is defined, and it is, of course, always a non-negative integer. It's always an integer. It's defined as index, which is a result of counting. It's non-negative integer. In particular, for constants, polynomials f, which are at the same time elements of the ring are just a naught and everything else is 0, the degree is 0, except one polynomial which is a constant and doesn't have a degree. In fact, one of the principal topics in this chapter is a similarity between the ring F, the polynomial ring, and the ring of integers. So we will find a similarity between the ring of polynomials over not arbitrary ring but field, and the ring of integers which we started in chapter 1. And the analogy goes this way. For a polynomial, its degree is kind of size, how big the polynomial is, a polynomial of high degree. For an integer, its size is the absolute value of this integer. So the analogy is based on that. So we have degree F for a polynomial is parallel to the absolute value for an integer. Both measure the size in some sense, and this analogy starts to be supported by the first theorem declared, which I want to declare. Theorem 4.2 in the book says that let R be an integral domain we are interested in a field. Every field is an integral domain, of course. So for a field, that's going to be true. Let f and g be two elements of R of x, two polynomials, and both non-zero. We assume that f is not 0 and g is also not 0. So that both of them have degrees. Then degree of their product Fg is equal to the sum of their degrees. that is a similarity here is with an obvious statement and the ring of integers. We have that AB for any two integers is equal to the product of the absolute values. It doesn't look very similar. This is a product and this is a sum. However, in any case, in either case, we have this. And that is what we actually need to know about the degree. This is good to know, we will use it, but what sometimes is more important that, a weaker statement, degree of the product is bigger or equal than degree of a factor. Of course, I can put g here, that stays true, and here I have that the absolute value of the product, assuming now a is not 0, b is not 0, is bigger or equal than the absolute value of a factor. Now I need this assumption, I didn't need it here, and under this assumption we have absolutely same inequalities. Degree of a product is bigger or equal than the degree of a factor. Any factor. Same thing with g instead of f in the right, b instead of a, also possible here. The proof is very easy, but first of all, I want to mention an immediate corollary from the proof, or something you need possibly prove before, or claim before you claim the theorem, that the left-hand side is defined. This is a corollary from this theorem, corollary from its proof, the argument, or maybe from the theorem, taken very formally. If R is an integral domain, then so as the ring we constructed, the polynomial ring with coefficients in R. Well, indeed, if this was not true, we could not, the theorem is not wrong. It makes no sense. It may happen that the right-hand side is defined, degree of two non-zero polynomials, degrees are both defined, while in the left we'll have a degree of 0, which we don't know what is that. So as soon as we actually prove the theorem, we get that the product Fg has a degree, therefore it is not a 0. Here's the proof of the theorem. I will only roughly tell you how to prove the theorem, because the argument is quite simple. You may read, and you should probably read some details in the book. So, proof of the theorem. What should we do? We should look at the leading coefficients. So we write both polynomials f to be a naught plus, so father plus a n x to the n. We write g to be b naught plus dot dot plus bm x to the m, and in this way we have the assuming degree f is n and degree g is m. So we write the polynomials so that the last coefficient, the leading term, is non-zero. That means assume degree f is n, then f can be written in this way with non-zero an. Same about g. Now we use our definition of the product and find, by definition of the operation of multiplication in the polynomial ring, we find that fg, the product, is a naught b naught plus many other coefficients plus an bm x n plus m. Now we assumed here an is not 0 and bm is not 0. Since R is an integral domain, the product of two non-zero elements is non-zero. And now, by the definition of degree, this coefficient, an times bm, being non-zero, is the degree of fg, the product. Thus, the degree of fg is, we simply read it n plus m from here, which is the degree of f plus the degree of g as required. The theorem is proved now. So, again, to our analogy between the ring of polynomials over a field and the ring of integers. So, there is a similarity, there are differences. In Z in the ring of integers. We know everything about units, and that is very simple. The only units are invertible elements, are 1 and -1. All other integers do not have multiplicative inverse. And this ring, it is different. There are other units besides 1 and -1 in the field, but the situation is still under control. Here is corollary 4.5, which describes units in this ring. In fact, the corollary is formulated a little bit wider in the book. Let R be again an integral domain. An element, a polynomial, is a unit if and only if f is an element of R. This is a subring, a subset of R of X, and f is a unit in R. So it's a polynomial of degree 0, a constant. And this constant must be a unit in our integral domain, an invertible element. The corollary in the case of interest, in the case of a field, sounds even simpler. In particular, for a field f. A field is always an integral domain. Not every integral domain is a field. A polynomial with coefficients in the field is a unit if and only if what kind of integral domain is a field? First of all, we copy the first requirement, that our polynomial is a constant polynomial, and the second requirement becomes way simpler. A field is an integral domain such that every non-zero element is a unit. So instead of writing is a unit, how do you check whether some element in an integral domain is a unit? You have to study this particular integral domain. In Z, there is a huge amount of non-zero elements, all of them except 1 and -1, which are not units. However, Z is an integral domain itself. However, filled as is an integral domain when such that every non-zero element is a unit. So the condition to be a unit in a field means simply f is different from 0. So all constants except 0 are units in the polynomial ring, all elements of the field. All polynomials of degree 0 are units. The proof is very simple, and it's written in the book. I cannot add anything to this proof. It follows from adding 2 degrees. So basically, the key moment of the proof is, so for the I will only highlight the key moment. So from the proof, that is when we assume that f is a unit, then we want to prove that f is a non-zero constant. Then, by definition, what does it mean a unit? Fg is identity in R of x, which is the same as identity in R, as probably is clear. And now we think about, well, now we're taking into the account the theorem just proved. Fg is a product of 2 polynomials for some g. So for every unit there exists an inverse. That is what is written. On the right, this identity 1 is a polynomial of degree 0. This is a constant. On the left, it is a product of 2 polynomials. So by the theorem 4.2, we can write that degree f plus degree g, which is the degree of product, that is what's proved in the theorem, is equal to the degree of the polynomial in the right. So fg is 1. What is the degree of constant? This is 0. Now we have a sum of 2 non-negative numbers, which is 0, meaning both of them must be zeros. Thus, therefore, degree f is equal to degree g and is equal to 0. Thus, f must be a constant. After that, that's routine to check that f must be not just arbitrary constant but a unit, g as well, and the converse statement that if f is a unit, then if f is a unit in the ring R, then it is a unit in this ring, is more or less straightforward. So this is only the interesting moment from the proof. We use the identity Fg equals identity take this as this is constant polynomial of degree 0. This is a polynomial. Degree of the product of two polynomials is sum of their degrees. Now we have sum of two non-negative numbers, which is a 0. That implies that both of them must be 0, otherwise the sum is going to be strictly positive. Thank you for listening. In the next fragment, we'll already assume that our base ring is a field and look at the polynomials over a field.